Active mode operation. JFET's characteristic curve. A JFET's characteristic curves display the same current regulating behavior as for a BJT, and the nonlinearity between gate-to-source voltage and drain current is evident in the disproportionate vertical spacings between the curves. To better comprehend the current regulating behavior of the JFET, it might be helpful to draw a model made up of simpler, more common components, just as we did for the BJT. In the case of the JFET, it is the voltage across the reverse-biased gate-source diode which sets the current regulation point for the pair of constant current diodes. A pair of opposing constant current diodes is included in the model to facilitate current in either direction between source and drain, a trait made possible by the unipolar nature of the channel. With no PN junctions for the source-drain current to traverse, there is no polarity sensitivity in the controlled current. For this reason, JFETs are often referred to as bilateral devices. A contrast of the JFET's characteristic curves against the curves for a bipolar transistor reveals a notable difference. The linear, straight portion of each curve's non-horizontal area is surprisingly long compared to the respective portions of a BJT's characteristic curves. A JFET transistor operated in the triode region tends to act very much like a plain resistor as measured from drain to source. Like all simple resistances, its current-to-voltage graph is a straight line. For this reason, the triode region, non-horizontal portion of a JFET's characteristic curve is sometimes referred to as the ohmic region. In this mode of operation where there isn't enough drain-to-source voltage to bring drain current up to the regulated point, the drain current is directly proportional to the drain-to-source voltage. In a carefully designed circuit, this phenomenon can be used to an advantage. Operated in this region of the curve, the JFET acts like a voltage-controlled resistance rather than a voltage-controlled current regulator, and the appropriate model for the transistor is different. Here and here alone the rheostat, variable resistor, model of a transistor is accurate. It must be remembered, however, that this model of the transistor holds true only for a narrow range of its operation. When it is extremely saturated, far less voltage applied between drain and source than what is needed to achieve full regulated current through the drain. The amount of resistance, measured in ohms, between drain and source in this mode is controlled by how much reverse bias voltage is applied between gate and source. The less gate-to-source voltage, the less resistance, steeper line on graph. Because JFETs are voltage-controlled current regulators, at least when they're allowed to operate in their active, their inherent amplification factor cannot be expressed as a unitless ratio as with BJTs. In other words, there is no beta ratio for a JFET. This is true for all voltage-controlled active devices, including other types of field effect transistors and even electron tubes. There is, however, an expression of controlled drain current to controlling gate source voltage, and it is called transconductance. Its unit is Siemens, the same unit for conductance, formerly known as the mho.